Okay, this video is part 4 of in a series of videos on classification of linear second order PDEs. In part 1, we lay the foundation for the theoretical framework. In part 2, we worked on A and B. And then in part 3, we worked on C and D, and we gave you E and F to have a go, just something to enable you to see whether you are understanding the ideas. In this part 4, we're going to work through E and F, and so from our working you can now compare with whatever answer you have there. So let's start with E. So the PDE is 3uxx plus uxy minus 2yy plus ux plus uy equal to 0. So in terms of the classification, we're going to work out the discriminant. This is our A, B is 1, and this is our C. So that means the discriminant is going to be B squared minus 4 times 3 times negative 2. This is going to be 12 times 2, which is 24 plus 1, 25. This is bigger than 0. So this is telling us that the PDE is hyperbolic. Okay, so that is everything. That is all as far as the classification is concerned. And then in terms of reducing the PDE to canonical form, we need to work out the canonical coordinates. We start by solving the characteristic quadratic equation. So in this case, it's going to be 3 lambda squared minus lambda minus 2 is equal to 0. Solving this gives us 3 lambda plus 2 into lambda minus 1. So this is telling us that lambda 1 is negative 2/3 and lambda 2 is 1. Then from this, the characteristic ODEs, there's going to be 2 of them. First one is going to be dy dx is negative 2/3. This is telling us that 3 dy plus 2 dx is equal to 0. Integrating this gives us 3y plus 2x equal to c1. So this is going to be our first canonical variable or coordinate. Then the other one, dy dx is equal to 1. This one tells us that dy minus dx is 0. And so y minus x equal to c2 is eta. In fact, in our working, we have x minus y. So let's do x minus y here, so that, but even if we do y minus x, solution is still going to be perfectly okay. Then the first order derivatives of these canonical variables with respect to x and y, xi x is going to be 2, xi y is going to be 3, eta x is 1, and eta y is -1, which means that the second order partial derivatives will be 0. The Jacobian is going to be 2 times -1 minus 3 times 1. This is going to be -5, non-zero, so that means our coordinate system is okay. So it means it's locally invertible. Okay, so then using the chain rule, ux is going to be 2 times uxi. The 2 is the derivative of xi with respect to x. This is going to be plus eta, that is 1 times u eta. And then from our previous video, we said the uxx coefficients are going to be binomial like. So the coefficient for uxi is going to be the square of this, which is 4. The coefficient of the mixed derivative is going to be 2 times this number times that number. It's going to be 2 times 2 times 1. So that is going to be 4 as well. And then the coefficient of u eta eta is going to be the square of this coefficient, which is 1. So it remains like that. And then none of the first order derivatives is going to appear because our coefficients here are constants. The first order derivatives only appear if these are not constants. All right, then we go to uy. For uy, there is xi y. So we're going to have 3uxi, and there is eta y, which is -1. So we're going to have minus u eta. And then again, uyy is going to be the square of 3, which is 9, minus 2 times 3 times negative. Okay, 2 times 3 times 1, the minus is already there. So this one is going to be 6 uxi eta, and then the last one is going to be that. Okay, then we do the mixed derivative uxy. So the coefficients for that one we just get from these two first order derivatives again. Now notice that if we multiply these two coefficients, we get 6. So that's going to be the uxi term, the coefficient of the uxi term. And then for the mixed derivative, we simply do the sum of the cross multiplied coefficients. So we are going to have 2 times -1, which is -2. Then we're going to have 3 times 1, which is 3. So that means the coefficient of this is 1. Okay, and then for the last one, we just simply multiply the coefficients of the u eta terms. So that's going to be minus u eta. We now have all the derivatives, so we're going to substitute into the PDE. So the PDE becomes, so the first term in the PDE, remember, is 3uxx. Okay, so we got 3uxx plus uxy minus 2yy. So we're going to have 3uxx, which just worked out is uxi xi, 4uxi xi plus 4u xi eta plus u eta eta. Then this is plus uxy, which we've just worked out, 6u xi xi plus u xi eta minus u eta eta. Then the last term is minus 2uyy. So that one was 9u xi xi minus 6u xi eta plus u eta eta. Then we have got ux, which is 2uxi plus u eta. Uy is 3uxi minus u eta. All right, then we collect terms. So let's start with the uxi xi. Now remember, if this thing is hyperbolic, we are expecting that only this term is going to survive from the second order terms. All the other terms we expect to cancel out. If they don't, then it means there's something wrong that we have done, which we need to go and sort out. So from here we've got 12 of these plus 6, we've got 18, then minus 2 times 9 is 18. So these terms cancel out. Then the uxi eta terms, which we expect should give us non-zero term, we have got 12 here, and then we have got 13 here. Then it's going to be minus 12. So that is just going to be u xi eta. And then the u eta eta terms, we've got 3 here, minus 1, so we're down to 2, then minus 2, then we're down to 0. So those cancel out as well. And then the u eta and minus u eta cancels out. So this is going to be plus 5u xi. So that is our canonical form of the PDE. Before we go to part 3 to solving this, I'm just going to make a note about the canonical coordinates. So you got to remember, here we have got xi is equal to 3y plus 2x equal to c1. And then we have got eta equal to x minus y equal to c2. Now, so what these coordinates are saying is this, or what this analysis is telling us is the following. So if we start off with the xy coordinate system, okay, in this coordinate system, the equation, the PDE is 3uxx plus uxy minus 2uyy plus ux plus uy equal to 0. Then if we introduce a new coordinate system, okay, defined by these excuse me. So let me just take the eta coordinate variable, for instance. If c is 0 here, then this is simply x equal to y. Okay, so that is the line eta equal to 0. If c is equals to 1, this thing is going to give us y equals x minus 1. Okay, so basically this is going to give us a set of parallel lines. This is eta equals to 1. It's going to be eta equals to -1 here, like that. Okay, so these are the eta equal to constant set of lines. Then the xi equal to a constant lines are going to be going in the other direction. So these are positive gradient lines. These ones, if c1 is 0, for instance, it's going to go through the origin. Okay, it's going to be y equals to 2/3 x negative. So it's going to go something like this. Let me use this color. Okay, so that's going to be something like this. This is xi equals to 0. If xi is equal to 1, then it's going to be something like that, xi equals to 2. So this is going to be the coordinates of the canonical coordinate system, eta or xi eta. Now so let me just make another sketch here. So if you take just one moment. So this is our original xy, then the new coordinate system, if we take the eta equals to 0 and the xi equals to 0 to be our new coordinate axes, then they are going to look something like this. So this is eta equal to 0. This is xi equal to 0. Just like in the xy coordinate system, this axis is y equal to 0, and this axis is x equals to 0. Then you get a a sequence of these are lines, say y equals to 1 here, 2 here, 3, and then this is x equals to -1, -2, and then from this you get these rectangular boxes or rectangular systems. And then each line, or rather each point, is identified by sort of specifying the corner or a unique corner of a unique rectangle. Okay, so in this case, these are going to be our xi or eta equal to a constant lines, and you can see that these ones are forming into some kind of parallelograms or kites or something like that. And then each point is going to be specified by so for instance 0, 0 is going to be the same as before, and then maybe this could be 2, 1, 2 this way, 1, 2 this way, 1 this way. So if we define the coordinate system like this, okay, then this PDE simply becomes what we found here, which is a much simpler PDE. So in terms of this coordinate system, the PDE becomes u xi eta plus 5u xi equal to 0, which is much easier to integrate. So we take the PDE, we transform it into this coordinate system, which is the canonical variables, and then we get a simplified or the canonical form of the PDE, and then we integrate it. Okay, yeah, so we thought let's just comment about the theoretical framework of these canonical variables. So you take the PDE from your rectangular coordinate system xy to your canonical coordinate system xi eta. The PDE simplifies considerably, and then we can now integrate it. So in part 3, this we can write as partial xi of u eta plus 5u equal to 0. Integrating with respect to xi gives us u eta plus 5u equal to f of, so we integrated with respect to xi, so it's going to be f of eta. Then here the integrating factor is going to be e to the 5 eta of multiplied both sides by e to the 5 eta. This is what you're going to have. This is partial eta. Then we can integrate now both sides with respect to eta. So this side is going to be u times e to the 5 eta equal integral of this, which is just going to be another function of eta. So let's say this is plus g of xi now. And then if we multiply through by e to the 5 eta, e to the negative 5 eta, so this is going to be e to the negative 5 eta integral of e to the 5 eta e to the minus 5 eta g of xi. This is all just a function of eta, so we can write this as f of eta plus e to the minus 5 eta g of xi, from which then this in terms of x and y is going to be f of eta is x minus y, and so that's going to be e to the minus 5x minus y g of xi. Xi is 3y plus 2x. So g and f are arbitrary functions here, and so this is our final solution in terms of x and y. All right, we're now going to go to the last one, which is f. So in f we have got x squared uxx minus y squared uyy equal to 0. X must not be 0 and y must not be 0. So this PDE is defined away from the coordinate axes. So the discriminant, which is b squared, b is 0, minus 4ac. So this is just going to be 4x squared y squared. Is going to be definitely greater than 0 because x and y cannot be 0. So again, this is telling us that the PDE is hyperbolic. Okay, Then in part 2, the characteristic quadratic equation going to be x squared lambda squared minus y squared equal to 0. If we solve this, we're going to find that lambda is plus or minus y over x. Then the characteristic ODEs, there's going to be two of them. The first one is going to be dx dy equal to y over x. So this is the same as y prime minus y over x equal to 0. This is linear. The integrating factor mu is going to be the exponential of the integral of minus 1 over x, which is just going to give us 1 over x. So that means this thing, we can write it as y over x prime equal to 0. So y over x is equal to c1 when we integrate, which is going to be our xi. Then the second one, dy dx, is equal to negative y over x. So this time we've got y prime plus y over x. This time the integrating factor works out to x. So this thing we can write as xy prime equal to 0. Integrating, we get xy equal to c2. So this is our eta. Then in terms of the Jacobian, xi x is going to be minus y over x squared. Xi y is just going to be 1 over x. Eta x is going to be y. Eta y is going to be x. So the Jacobian is going to be minus y over x squared times x minus 1 over x times y. So it's going to be minus 2y over x. This is not going to be equal to 0 because neither x nor y is 0 in this PDE. Okay, we can now start working out the partial derivative of u. So ux is going to be this term times uxi. So minus y over x squared uxi. Then plus is going to be this term times u eta. Now, then the second order derivative. So the second order derivative terms are just going to be given as before. So the square of these is y squared over x to the power 4 uxi xi. And then the mixed derivative term, we just multiply these two coefficients and multiply times 2. So 2 times this times this. It's going to be minus 2y over x. It's going to be minus 2y over x. U xi eta. Then the last term is going to be the square of this, which is x squared u eta eta. Okay, start 1 minute. Okay, you're going to have to forgive me. There is just a small error here. Here we multiplied by the derivative of eta with respect to y. Surely it's supposed to be the one with respect to x, because this is the x derivative. So this is going to change, and that is going to change. So this is y here. Okay, and so that is going to be minus 2y squared over x squared, and this is going to be y squared. Okay, however, notice that this time we are going to have a first derivative term because of this x here. So when we differentiate this again with respect to x, we have got to differentiate this using the product rule. So if we differentiate, we multiply by -2, so it's going to be 2y over x cubed, and then we just keep this fixed. All right, okay, then we go to the y derivative. So for the y derivative, we're going to multiply by xi y, so that's 1 over x uxi. Then now we are going to multiply by this one, so that's going to be xu eta. So then uyy going to be the square of this, then plus 2 times this coefficient times this coefficient is 1, then plus the square of this coefficient u eta eta. Now, since these coefficients do not involve y, we won't have a first order derivative term here. The ODE only involves uxx and uyy, so there's no need to work out uxy here. So sorry, the PDE. So substituting, so the PDE becomes, so we simply multiply the first one by x squared. So multiply this one by x squared, multiply this one by y squared, and subtract. So if we do that, so x squared uxx, which is going to multiply through here by x squared, so that's going to be, the first term is going to be y squared over x squared uxi minus 2y squared uxi eta plus, we are multiplying by x squared y squared u eta eta. Then the last term is going to be 2y over x, just x, then uxi. Then we multiply the uyy by y squared, so we're going to have y squared over x squared uxi plus 2y squared uxi eta plus x squared y squared u eta eta, and then we subtract. So x squared uxx minus y squared uy, y is going to give us, this term cancels out, this term cancels out, these two terms add. Okay, so we're going to have negative 4y squared uxi eta plus 2y over x uxi. This is equal to 0. So if we divide through by -2, this is going to be 2y squared u xi eta plus y over x u xi is equal to 0. Notice that we could have divided by y, especially because y is non-zero. But as we do this, we have one eye on the canonical variables, and being able to express the canonical equation in terms of xi and eta only. So here we know that y over x is xi, so that means if we leave this like this, we can already write it in terms of xi. So actually let's do that. So this is xi u xi, okay, equal to 0. Then question is, what is y squared in terms of the canonical coordinates? So this is y over x, this is x times y. How can we eliminate x from here and get y squared? You're going to notice that if we just multiply these two, then x cancels out and we have y squared. So this is going to be 2 xi eta u xi eta, okay. And then now we can divide through by xi. So this is going to be 2 eta u xi eta plus u xi equal to 0. So that is our canonical form. Now let me just quickly talk about the canonical coordinates. Okay, so this time, if this is our xy rectangular coordinate system, the xi coordinates are going to be given by so we've got xi equal to x over y equal to c. Okay, well, so if you like, this is just y equal to a constant times x. Okay, so these are just going to be straight lines going through the origin. As c changes, the gradient changes. So for instance, if c is 1, it's going to be like this. If c increases, then the gradient becomes smaller and smaller. C is -1, and then so this is just going to be rays of lines emanating from the origin, a bit like your angle equals constant in your polar coordinate system. Okay, so these are the xi equal to, so for instance, this is xi equal to 1, this is xi equal to -1. Okay, then the eta, so the eta coordinates, so eta is xy equal to constant. So these ones are y equals to c2 over x. These are hyperbolas. Okay, so these ones are going to go something like this. Okay, so this is the case where c is positive there in the first and third quadrants. If C is negative, they are in the second and fourth quadrants. So for instance here, C or eta equals to 1, etc. So this is going to be what your canonical coordinate system is going to look like. In the xy coordinate system, the equation is given by this. In the xi eta coordinate system, the equation is given by that. The main thing is that this is integrable, as we will demonstrate just now. So part 3, we have got 2 eta u xi eta plus u xi equal to 0. So this we can integrate with respect to xi. It gives us this. So we just integrated with respect to xi. So this is going to be a function of eta. And then if we divide everything by 2 eta here, 1 over 2 eta, 1 over 2 eta, then we can find the integrating factor. It's going to be the integral of d eta to eta. This is simply going to be 1 over square root of eta. Just make sure that you can go through those steps. So if we multiply this whole thing by 1 over square root eta, so it's going to be 1 over 2 eta square root eta. Then the left hand side is going to be integrable. So that becomes that. Then we integrate that whole thing there. D eta. This is going to be plus a function of xi, which is going to be arbitrary. Then u is going to be square root eta times this integral, which we don't have to evaluate. Well, we can't evaluate actually, even if we wanted to, because f is arbitrary. And then our u is f of eta plus square root of eta times g of xi in terms of x and y. So this is f of eta is xy, square root of xy here, and then xi is y over x. So this is going to be our final solution. It looks like there's going to be a part 5 of this video series. In part 5, we are going to revisit part B. Okay, I'll tell you what happened in part B. In part B, I'll revisit part B. In part B, we had this PDE 4u xy, 4uyy equals to e to the y. We found that this PDE is parabolic. So if it's parabolic, there is only one coordinate, canonical coordinate, that comes from the characteristic ODEs. Then we chose eta to be equal to y, and we worked it out. We said this can be chosen to be anything so long as the Jacobian is different from 0. Well, a question could be, what if we choose a different function from y? Okay, what if eta is chosen differently? Okay, so in part 5 of this video series, we're going to answer this question. We're actually going to make two different choices of eta and show you that it still doesn't change the functional, the form of the equations are going to be slightly different, but when you integrate to the end, then you find that your solution should be the same in principle. Okay, so we'll show that in the part 5 of this video series. Okay, hopefully this has been useful. Thanks for watching. You can subscribe so that you can get notified whenever we post new material. Thank you.